Hello and welcome back. This is the latest video in our alignment foundation section where we cover the why, what and how of biomolecular sequence alignment. Now last time out we introduced and indeed walked through the classic dynamic programming approach for so-called global alignment. Here we'll discuss the adaptation of this approach to local alignment, and we'll describe what these two terms mean and also how this local alignment method can be used for database searching and how it's used, for example, in the heuristic Smith-Waterman approach employed by BLAST. Now, the Needleman and Wunsch global alignment algorithm that we presented last time, it involves taking two sequences, building on our dot plot approach by forming a matrix of dimensions m+1 and n+1, that is, n+1 rows and n+1 columns, where m and n are the lengths of the two sequences that we're going to consider or compare in this approach. And then in that first row, in that first column, that +1 rows and columns, here we use a gap penalty for each position. So in this case it's -2, and we sum them up as we go down that first column and across that first row. -2 plus -2 plus -2, etc. for the lengths of the two sequences. Now then the fun starts. We use a predefined match and mismatch values together with that gap score to go through each position in this recursive approach and find the highest summation of scores when we consider the three possible routes to arrive at a value for the current score, these three possible calculations we can do. Those little calculations involve summing up with the values in either the preceding diagonal, that's in the upper left position relative to the one we're considering directly above, or the preceding left position. And what we do is we take the maximum of those three possible routes, put that value in the cell, and keep that pointer, that arrow that led us to that maximum score. Now, the overall goal of this approach, of all this shenanigans, is to find the path through the matrix, that's from that first empty position up there, that lets us obtain the maximal score. And that maximal score is found in the last position, down in the bottom right of our alignment matrix. Now this path will give us the optimal alignment over the entire length of both sequences, because it spans the entire matrix right from the first to the last position. In other words, it covers the sequences globally, both sequences globally from end to end. And thus it results in alignment that spans the complete sequences, right, end to end, just like this little graphic here. Now this is fine and totally appropriate when we're comparing closely related sequences like these two that are somewhat similar in length, like these two. However, for many practical applications, we actually want to highlight not end-to-end similarities of two sequences or global similarities, but subregions within two sequences that might align well. Now these two sequences might otherwise be unrelated outside these alignable regions, like the little graphic here, and they could be perhaps of very different lengths. For example, one could be a whole genome sequences that we want to align little fragment sequences to. It doesn't make sense to try and do a global alignment for these things. Now this is the job of local alignment methods. So these local alignment methods, they require some alterations to our approach in order to yield alignments that do not need to span the complete lengths of both sequences. Let's delve into those modifications now. So the first folks that really pioneered this approach, realizing the pressing need for subsequence matching as databases grew and longer multi-domain sequences started to be accumulated in these databases that we wanted to search, were Smith and Waterman. Back in the early 1980s, they proposed this first simple modification to the Needleman and Wunsch approach, published a decade earlier, that would allow arbitrary length subsequences to match. Basically, it boils down to not penalizing the unrelated regions in these sequences. That is, not scoring any positions with negative values, but rather just entering 0 in those cells of the matrix. So let's look at this in a little more detail. Now the three main modifications proposed by Smith-Waterman are: 1, to allow a node to start at 0. So what does that mean? Well, this is what it means. We're going to use 0 values for those first gap row and gap columns that we would have otherwise used the gap score for in the Needleman-Wunsch approach. We can start any of these positions with zeros, as we do here in Smith-Waterman. The second modification is that we're never going to put negative values into the alignment matrix. Now, the mechanics for calculating the thing is just the same as before, right? We score the positions by considering the three possible routes, right, from the diagonal, from the upper, or from the left position, and finding the maximum one. But if any of those routes return a value below 0, we forget about it. We stick a 0 in there instead. Okay, so that's this modification here. In yellow, we have this 0 route. If that's higher than any of the other three routes, we'll place a 0 in the corresponding cell that we're considering. Okay, so if we zoom in here, we'll still score things just the same. So in this particular value here, right, the second modification, that we're never going to put negative values in here, we'll still score things and go through cell by cell using the three preceding values just as before, but we have this extra condition highlighted in yellow here, where if we score below 0, as in this case, right, we've got our position 1 that would yield a negative value that's going from the diagonal, position 2 coming from straight across, this yields a -2, and the same thing for going from the left position. They're all below 0, so we stick a 0 in that box. And we go through in the same fashion until finally we've finished filling in the entire matrix here, keeping the pointers or our arrows or directions where we had them, where we didn't use these 0 values, for example. Now, our final modification with Smith-Waterman is when we're finished filling in the matrix, we're not going to start from that happy place, that end cell, that last position cell where the optimal score would be in Needleman-Wunsch, but rather we're going to go into the matrix and find the highest score wherever it may be in the matrix and trace back from it until we hit a 0 value. That highest score value will be the best that we've got, right? So in this case, we'll find the highest score value. It's this position here highlighted in red, corresponding to this G with a G here, and we'll trace back from it for as far as we can go until we hit a 0 value. And what this will yield, as we follow back from this position here all the way back until we hit a 0, is our local alignment that yields a score of 3. So where these local alignments are particularly useful is in searching databases for related sequences to a query sequence. Now, the goal here in database searching is, we've got a query sequence, we'll call it Q here. For example, a sequence of a known function from some nasty beastie that we've discovered, on the bottom of our shoe or something, walking through the Amazon or whatever. And a sequence database, we'll call it D here, of well-annotated or comparatively well-annotated sequences that we know something about, that the literature has accumulated information on, for example. And we want to find a list of sequences from that database, those well-annotated sequences, that are most similar to our query, because it'll allow us to learn something about our query sequence. So the output from these database searching methods will be a ranked list like the one shown here, where we can infer something about the most similar sequences and what that might mean for our query sequence. So in this case, for example, our query is more likely to be a RAS protein rather than a heat shock protein, a HSP90 or a P450 protein, for example. Now, unfortunately, as databases in the mid-80s and later started to grow at these exponential rates, doing straight Smith-Waterman was just too slow to be useful. So to reduce the search time, we needed to use little shortcuts, we call these shortcuts heuristics, to make things more tractable. So for example, the common and well-known BLAST algorithm, it uses a modified form of Smith-Waterman that first removes database sequences without a strong local similarity to the query sequence in a quick initial scan. So it does this pre-scan of the database to remove things that are not likely to yield good alignments. In effect, what this pre-screen does is reduce the search space, because now we don't need to consider every sequence in the database, but only those most likely to give good answers. This smaller fraction, for example, in a pre-screen here where we looked which query sequences have this GVK little word within them, And then only those sequences will go forward for more exact matching with a Smith-Waterman style approach. So this pre-filtering reduces the search space and speeds things up pretty dramatically. So this pre-filtering approach, it lies at the heart of BLAST, which stands for Basic Local Alignment Search Tool, and it's a simplified form of Smith-Waterman alignment that's popular really because it's fast and it's easily accessible online, as well as in a downloadable form that you can install on your own computer. Now BLAST, as I've said, it saves time by restricting the search space, by scanning the database sequences for likely matches before performing more rigorous Smith-Waterman style alignments. So it's going to sacrifice some sensitivity in exchange for speed. So in contrast to Smith-Waterman, it's not guaranteed to find optimal alignments in every case, because we might have removed some sequences that would otherwise form good alignments because they didn't have this word match, for example. So as Stephen Ashton so clearly put it, one of the original authors of this approach, is the central idea of the BLAST algorithm is to confine attention to sequence pairs that contain an initial word pair match. This is just like that window approach we talked about a couple of videos back when we were first looking at dot plots, how we could speed up our dot plot approach and how we could pull out more signal from the noise, for example. We can do that with a windowing approach or a word approach, where the word is the window, or they call them k-mers or k-tuples, where k is the length of the window here in the BLAST terminology. So in practical terms, this pre-screening, looking for these initial word matches that computers are very quick at. Computers have been matching text and exact words for a long time, and they don't require any of this kind of dynamic programming approach to do it. Practically, this results in around a 50 times speed up for most typical databases that we have around today. So 50 times faster than doing conventional Smith-Waterman, for example. So how does BLAST work in detail? Well, there are 4 basic phases for how BLAST works. First phase is it generates an exhaustive list of words, what it terms k-mers, where k is the number of letters, for the protein that we're going to search with. So for example, in this protein here, the BLAST default is to use words of size 3 or k-mers of size 3. It generates all possible words here. Then, in the second step, k-mers similar to the original query are added. So this extended list is then used to search for perfect matches to these words in the query sequence. So if any of the database sequences have this k-mer, it's matched and it's used as a seed for local alignment. This terminology seed comes from the original BLAST literature. Basically, the seed then is an anchor in the 2 sequences, the query sequence that we're searching with and the database sequence that we found this word in. And we're going to use these positions then to start our Smith-Waterman alignment, because we can initialize that first column and that first row with zeros from the ends of these seeds. We can start doing our Smith-Waterman just from these seed positions or anchor positions. In effect, it looks a little bit like this. We're going to extend this seed in both directions using good old dynamic programming that we've talked about. So zooming in here, we're going to look at the seed. This is our query sequence and our database sequence, and then we're going to extend through the matrix in these regions. We're going to focus on these subregions. Again, we're going to save time here because we don't have to consider these other regions. And we're going to search for these highest scoring alignments in these regions. And how are we going to do that? Good old dynamic programming, of course. So what BLAST will do with these seeds, it will return the seeds or what it terms highest scoring pairs above a user-defined threshold score. And it will return these highest scoring database hits and their local alignments in a ranked list that looks something like this. So note the statistics here. We have the score from the alignment, right? That's the highest score in the matrix. Something called query coverage. Now, what this query coverage is, it tells us how much of the original query sequence, in terms of percentage of its length or characters that were in it, whether it was nucleotides or in this case amino acids, were matched in the alignment. So how much of the query sequence features in that local alignment or that subsequence that is actually matched. So for example, if all the characters featured in the alignment, it would be 100% coverage. If only half of the characters featured in the alignment, it would be a 50% coverage. Obviously here, higher values of coverage are better because they cover more of your query sequence. So we'll come back to e-value in a moment. It's probably one of the most important, or arguably the most important value here in the table. We will describe it in more detail in a second. Then we have a sequence identity, or what's called maximum identity here from all these alignments. And this is, of those aligned positions, how many characters, in this case amino acids because it's protein, how many of these amino acids are exactly the same in the query sequence and the database hit. In other words, how many of those characters are identical. And again, higher values are better here. Finally, we have the accession number for the hit sequence in the database, so we could go pick it out from whichever database it was we searched against here. So let's focus on in this e-value, or what's known as an expect value. It's one of the most important numbers, if not the most important number in a BLAST output. Why is it so important? Well, it's important because it gives us some context. It tells us something about the statistical significance of each hit. You know, if you just had the score, what does the score mean? Is a score of 600 good? Is a score of 400 good? Sounds pretty high, right? But it all depends on your scoring scheme, your length, the database size, all these sorts of things. This e-value is going to be a guide for us. It'll tell us about the significance, or how much we should trust each one of these hits, essentially. So more formally, the e-value is the expected number of hits that are as good or better than the observed local alignment score, that's the score returned for this particular hit, if the query and database are random with respect to each other. So that is the number of alignments expected to occur by chance with a score just as good or better than the one we're talking about right now. Okay. Now, typically, only hits with e-values below a significance threshold that can be set by the user are reported. So this is equivalent to selecting alignments with a score above a certain score threshold, as we'll talk about in a moment. So let's think about this in a little more graphical way here. So in an ideal world, we would have something like this. We'd be able to set a specific threshold score for an alignment, like this blue dashed line here, that would clearly separate all the related sequences. That would be the alignments returning the yellow score distribution here. These are things that are related, things that we're after, things that we want, true positives here, from unrelated sequences. This would be the alignments returning the score distribution in gray here. These would be all the gobbledygook, all the random stuff, the false positives in our case. And we'd be able to draw this line and clearly separate these two worlds from each other. Now, unfortunately, often both these score distributions overlap. Now, what the e-value describes is the expected number of hits with a score above the threshold if the query and database were unrelated, i.e. they were gobbledygook. Okay? That is, it's an estimate of the number of false positives here. It's the fraction here in red of the hits that we don't want reported back to us. So we want this e-value here to be as small as possible. You know, in an ideal world, it would be 0, right? It would be no false positives here. Okay, so let's go back then and look at our BLAST result table from before. So each hit here has a score and an e-value and the coverage, etc. Now, the first three, as you can see here highlighted, have an e-value of 0. That's good, right? But for the last hit reported here, we have a score of 42.7, so it's lower than the other scores, of course, and it has an e-value that are higher than the others. It's an e-value of 0.03. So what this tells us is that a score of 42.7 or better is expected to occur by chance in 3 out of every 100 alignments returned. That's the e-value of 0.03. So do you trust it? Well, perhaps you want to think twice about it. If 3 out of every 100 is just gobbledygook, it's just gibberish, then maybe this is not such a reliable result. Okay, if you want to find out more about e-values, we can certainly talk about them on the Piazza and elsewhere, but what I would do is I would point you to this web resource to find out more about e-values. So in general, very small e-values are what we're looking for. E-values less than 0.005 are usually considered significant here. And I will point you to this online paper by Stephen Ashton and colleagues, The Statistics of Sequence Similarity Scores. It'll tell you about the extreme value distribution and where the equation comes from to calculate this e-value from the values returned from a typical alignment. So I'm going to finish here and summarize that we've covered how sequence alignment is a fundamental operation underlying much of bioinformatics. Even when optimal solutions can be obtained by these dynamic programming approaches, they're not necessarily unique or indeed reflective of the correct alignment, because we don't have a time machine, right, in most cases. Dynamic programming is this classic approach for solving the pairwise alignment problem. We've reviewed global and local alignment approaches and their major application areas, and we've introduced these heuristic approaches that are often necessary for scanning large databases and searching with methods like BLAST or from many genomic applications that we'll talk about later in our course. So I'm going to finish here with your to-do list. I'm requesting that you do some light homework this week. So as soon as possible, please try the hands-on lab session sheet. I've also placed some additional reading on our course website. This includes Sean Eddy's excellent and very short and accessible What is Dynamic Programming primer manuscript. There are also 2 graded homework items that I'm requiring you to complete before next Tuesday. This includes a light quiz that should not take up too much of your time, but it will help me judge how well I'm getting information across in this format, as well as a Needleman-Wunsch style alignment problem from the lab sheet that I want you to submit and return to us. You should now be able to do these dynamic programming, the global alignment style programming exercises, or dynamic programming exercises by hand at this stage. And then finally, for next week, please do sign up for DataCamp. DataCamp is an online learning environment that we'll use to learn the R programming language in our next few sections of the course. You'll receive an email to your UCSD email address with an invite link. Now, as always, please let us know in Piazza if you have problems or questions. The reason I want to point you to Piazza is that others will be able to benefit from the discussions that we have there and the problems that we solve together. And among other things, for example, we'll be able to provide an invite code and a link to DataCamp should that sign-up email not get to you or work or otherwise be filtered out by the spam filters, etc. So that's all for now. Thanks for watching. I'll see you in lab and in our next section of videos. Thank you.